Um, so last week we have already learned IV characteristic of glow discharge. So if we apply a voltage between a cathode and the anode in a quartz tube, in a discharge tube, and then we might generate plasma. We might generate plasma. So in the circuit, we can add a voltmeter and ammeter to measure the current flow through the discharge tube and voltage between the cathode and anode, so that you can plot an IV curve like this figure. And in this figure, the lower part is the discharge with very low current density. So in this region, the current density is very low. So in this region, it's difficult to generate a stable plasma. So one requires two energy sources to generate plasma. Right. So the one source is from the electrical field, and the other source is based on the analysis of the tungsten. Another source coming from the radiation source. Okay. So if you block the radiation source and just apply an voltage between cathode and anode, you might generate plasma, but the plasma is unstable. So you cannot get a continuous discharge. Okay. But if you increase the current or increase the current density in the discharge tube, you can start getting stable plasma. And this kind of plasma is named self-sustained plasma. Self-sustained plasma. So if the gas discharge tube achieve this condition, we can say that the gas reach a breakdown condition. So the gas change from insulating condition to a conductive condition, or from insulating state to conducting state. And this is gas breakdown. Okay. So after you generate the plasma, you can change the load so that you can get the discharge with different current density. So in the upper region, the discharge can be distinguished into several kinds. So this region includes subnormal glow, normal glow, and abnormal glow. So usually when we say glow discharge, we mean that we generate plasma in this region, subnormal glow, normal glow, or abnormal glow. So in industry, people use these plasmas to do materials treatment or etching or thin film depositions. Okay. So later on, our course will introduce PECVD based on normal glow discharge and sputtering based on abnormal glow discharge. Okay. And when you run the experiment, you can adjust the output from power supply, from a DC power supply. And usually we control the output current or output power from the DC power supply, so that you can get the discharges. But if you read the current, you can find out in this region. In this region, when the current increase, the voltage also increase. And this region is the abnormal glow. Abnormal glow. So by increasing the current from 10 to minus amp to 10 to minus 1 amp, okay, the voltage might change from few hundred volts to above 1,000 volts. Above 1,000 volts. And if you keep increasing the current, when the current reach around 1 amp or a little bit less than 1 amp, the discharge will change from abnormal glow to arc. Arc, okay. And arc is a very condensed and focused discharge. Focused discharge. And normal glow, for normal glow and abnormal glow, if we look at the cathode and the anode surface, we can find out the whole electrode, the surface of the whole electrode are covered with a thin glow layer, very thin glow layer, but cover the whole electrode surface. But if you got an arc discharge, you will find out the discharge will localize at a very small point, very small point. So the condition or the phenomena of the discharge change a lot. Okay, and in industry, people use arc to melt materials, or weld steel or weld, even try to weld metal with ceramic. So one can use the arc melting and arc welding for the application, for the different applications. Okay. So Thomson analyzed the electrical breakdown condition. So if the discharge tube reach an electrical breakdown condition, or in this slide, if the discharge fulfill with the Thomson criterion, and then one can just use a set of DC power supply to generate stable plasma. Okay. So the borderline for the self-sustaining and non-self-sustaining plasma is the breakdown condition. Is realized by the Thomson criterion or the Thomson analysis. Okay, so change from non-self-sustaining discharge to self-sustaining discharge. Okay, so when the gas reach the breakdown condition, the composition between the gas composition between cathode and anode change from neutral molecules or neutral atoms to partially ionized cation and electron. Partially ionized cation and electron. And the density of these ionized species is high enough so that the gas behave like a conductor. So this is also called gas breakdown. Okay. And if you have a solid material, an insulating material, then you can also apply voltage between the two electrodes on the surface of the insulator. So the insulator might also change from insulating condition to a conducting condition. And such phenomena is also named as breakdown. And most time we also name the insulator as dielectric material. Dielectric material. So the breakdown is also known as dielectric breakdown. If you have a solid material, okay. But if you have an insulating gas at the beginning, and then you apply a voltage between cathode and anode, and then all of a sudden the gas change from insulating condition to conductive condition, and then we know that gas reach the breakdown condition. Okay. So Thomson analyzed the breakdown condition in this discharge tube. So the important thing is the electron multiplication. So for the electron multiplication means that for if there is one electron starting from the surface of the cathode, and then when they travel toward the anode, the electron will gain energy from electrical field. So it means the energy of the electron will keep increasing when the electron travel from cathode surface to anode surface. And if the electron gain high enough energy, and when they collide with gas atoms, they might ionize the gas. So when the ionization happens, there will be new electron and ion pair. So from one electron to two electrons, and then more and more electrons. When the first electron travel across the gas tube to the surface of anode, okay, and this phenomenon is also known as the electron multiplication. Okay, so the electron multiplication is attributed to the increase in the energy of the primary electrons. Okay, here. So if the primary electron got high enough energy from the applied electrical field, they can ionize the gas molecule. Okay, and this equation can describe how many electrons or can the number of electrons increased. Okay, so if at the beginning there are n sub x electron, and when they travel for a distance of dx, the number of electrons increased, or dn equals to alpha times n sub x sub dx. Okay, so here is a coefficient alpha. Alpha is the mean number of ions formed by an electron in a path of 1 centimeter. Okay, so here is a parameter alpha. And if we start from the position at x at 0 and end at the position of x equal d, it means if the electron travel for a distance of d, okay, and based on this equation, we can know the increase of the number of electrons can be described by dn equal alpha nx dx. And the total number of the electron can be described by the equation if we integrate this differential equation, okay, from x equal 0 to x equal d. And then we can get the total electron density equal to the initial electron density times exponential of alpha d. Exponential of alpha d. Okay, and this figure shows the alpha over p against the E over p. So here alpha is the mean number of ions or electron and ion pairs formed by an electron, right, in the path of 1 centimeter. And E is the applied electrical field. Right? The horizontal axis is E divided by P. So this is normalized electrical field. Electrical field divided by the pressure of gas. Okay, and the vertical axis is the alpha divided by pressure. Divided by pressure. Okay, so from this figure you can see, in general, when you apply electrical field increase, alpha also increase. Right, in general, for these cases. So actually, alpha depends on the ionization energy of gas. Ionization energy of gas. Okay. So alpha depends on the ionization energy of gas and the energy of primary electron. And energy of primary electron. Okay. So when the applied electrical field increase, the energy of primary electron also increase. So the electron impact ionization will happen, and then there will be more and more electrons generated, electron and ion pairs generated. Okay. So the first part only consider that the ion and electron pairs are generated in gas phase. Okay, so that's the reason both energy of electrons and the ionization energy of gas species are important. Based on this analysis. And then the second important parameter is the secondary electron. Secondary electrons generated from the cathode surface. Okay. So if we look at the discharge tube again, when electron travel from cathode toward anode, right? The electron can collide with gas atom and generate electron and ion pair, right, by the collision process. And electrons, those initial electrons and generated electrons will keep traveling toward anode. But for the ions, cation has positive charge, so they will travel toward cathode. So eventually, ion will collide with cathode. The cation will collide with cathode. And the collision might also generate electrons from cathode surface. Okay. So for each cation colliding the cathode surface, there might be a small number of electrons coming out from cathode surface. And this parameter is the gamma parameter in the second part here. The gamma. Okay. Okay. So these ions, right? This ion arrive at the cathode surface, at the cathode surface, and extract the secondary electrons. So if one cation reach the surface of the cathode, the gamma of the gamma electrons will be knocked out, and this electron called secondary electrons or secondary emission. Secondary emission. So this is the second important part. The electron can also be generated from cathode surface after ion bombardment. After the ion bombardment. So, and if we look at the first part here, if one electron start from a cathode surface and travel to anode surface, the total number of electrons will change to exponential alpha d. Exponential alpha d, right? If at the beginning there's one electron, and then at the surface of the anode, there will be exponential alpha d of electrons, total number of electrons, starting from 1 to exponential alpha d. Okay, so that the electrons generated during the first electron traveling equals to the bracket, inside the bracket, exponential alpha d minus 1. Newly generated electrons inside the discharge tube. And also there will be a same number of ions generated, because electrons and ion pairs, right? Ion pairs are generated together in the discharge tube. Okay, so there will be exponential alpha d minus 1 of the ions, and the ions, when they come to the surface of cathode, they can extract gamma times exponential alpha d minus 1 secondary electron. Secondary electron, okay. So so when one electron, right, travel from the surface of cathode to surface of anode, when they come to this place, the number of electrons will increase to exponential alpha d, from 1 to exponential alpha d. And during this journey, there will be a exponential alpha d minus 1 of electron and ion pair. So maybe in this place, okay. Here's one. One electron from the cathode surface, and then when the electron travel to the anode surface, the total number of electrons become exponential alpha d, right? And then we can calculate the newly generated electrons and ions. The number of newly generated electrons and ions equals to exponential alpha d minus 1. Okay. And for these ions, the ions will travel to surface of the cathode. So all these ions travel to the surface of cathode. And for each ion colliding the surface of cathode, they can knock out gamma electrons. Knock out gamma electrons, okay? Knock out the electrons. So the newly generated electron from the cathode surface, or the secondary emission or secondary electron, equals to gamma times exponential alpha d minus 1, right? So the newly generated electron from the cathode surface. And then this electron will also travel toward the anode, and also generate electron and ion pairs. And this reaction will keep happening. So when we calculate the total number of electrons and the ions, they should be like this series equation. So that the total number of electrons from a single initial electron in a discharge tube equals to exponential alpha d plus gamma times exponential alpha d minus 1 times exponential alpha d, and then the second and the third term, here's a series, okay? And this series equals to exponential alpha d divided by 1 minus gamma, and in the bracket exponential alpha d minus 1. So this is the multiplication. M means the multiplication. So from this analysis, from Townsend's analysis, if we start from single initial electrons, we can get the M electrons. Okay. This is called multiplication. M is the multiplication coefficient of the discharge. And if we look at this side, we can find out if this denominator approach 0. If this part approach 0, the M will approach infinite. And this causes the electrical breakdown. So for this denominator equals to 1, equals to 0, and then gamma times exponential alpha d minus 1 should be equals to 1. And this equation is named Townsend criterion. For breakdown. So if you can generate a plasma with this condition, you can get self-sustaining plasma. Self-sustaining plasma, it means you only need one power supply to generate plasma. You don't need the second power source. You don't need a second energy source. So you don't need the extra source from the cosmic rays. You don't need this part. You can make a closed system and generate plasma inside your chamber just by applying the electrical field, apply the voltage between cathode and anode. Okay. So that one can get self-sustaining plasma, right? The upper region of this IV curve, self-sustaining plasma. Okay. So the condition to reach self-sustaining plasma or to reach the breakdown condition is named Thomson criterion. Okay, Thomson criterion, gamma times exponential alpha d minus 1 equal 1. Or you can also write down another way, gamma times exponential var epsilon v minus 1 equal 1. And var epsilon is the first Thomson coefficient. Gamma is the second Thomson coefficient. Thomson coefficient. So you can get these two coefficients from some handbook or textbook. If you study the DC glow discharge, okay. And since the gamma factor, the gamma factor here, gamma, right, correlated to the secondary electron emission from the material surface. So if you use different materials as the cathode material, you will get different gamma. Okay. So for some metals, if you use some metals as the cathode surface, as the cathode, you might get plasma easily. And if you use another metal, you might need a very high voltage to generate plasma. Okay. So gamma is only dependent on the material, on cathode material. And alpha or the var epsilon depends on the energy of primary electron, which is related to the dimension of your system, and also depends on the ionization energy of gas. Okay, so later on we can find out if you want to generate argon plasma, it's easy, but if you want to generate nitrogen plasma, it's very difficult. It's very difficult to generate nitrogen plasma because the nitrogen has a much higher ionization energy than argon. Okay, so this is the one of the important analysis, Thomson analysis for the breakdown. Okay. And then following the Thomson analysis, patient, another one is the patient, analyze the discharge, and from these empirical curves, one can use the simple model to fit this alpha over E or alpha over P against the E over P curve to fit the left part of this curve. So the curve can be described by this equation. So the left side of the equation is normalized alpha. It's alpha over P. P is the pressure, right? And on the right side, the variable is electrical field over P, E over P. So the curve can be described by this equation, alpha over P equals to A times exponential bracket minus B over E over P. Okay. And the reason why the curve doesn't use alpha against the E, but rather use alpha over P against the E over P, because pressure is also an important factor in the glow discharge. Okay, so remember in the last part of the nature of plasma, part 1, we learned that one of the important parameter is the Debye length. Debye length, right? Debye length is how far an electron can affect other charged particles. And the other important length parameter is the mean free path. Mean free path. So in the mean free path gave us a distance, a distance that gas can travel freely, right? Before the gas collide with another gas. Okay. So when we generate plasma, we need high energy electron. And the energy of the electron, right, is supplied by electrical field. So if the electron travel for long distance, right, in a uniform electrical field, the electron will gain higher energy. But if there are a lot of gas atoms, when the electron travel for a short distance, electron will collide with the gas atom. So the energy of the electron in a fixed electrical field depends on pressure. So if the pressure is high, there are a lot of gas atoms. The gas density are high, so that the electron cannot travel for a long distance. So the effective energy of the electron will become smaller. So that's the reason right here, the electrical field is normalized by pressure, divided by pressure. Okay. And for the vertical axis, alpha is related to the ionization process. Right? So if electron collide with gas atom, electron can ionize gas, right? And if the gas density is very low, the collision probability becomes smaller. Electron needs to travel for a very, very long distance to meet a gas atom. So usually, when the gas density is high, the collisional process can be more. So that the chance for the ionization will increase if the gas pressure is high enough. Okay. Okay, so from Townsend's semi-empirical relation, Paschen used this equation to fit the curve, and then further derive the breakdown voltage required for the gas discharge system. So Vs is the breakdown voltage. Right? The voltage we applied between cathode and anode. Right? So when we run the experiment, we can increase the applied voltage gradually, and then all of a sudden, the gas become conductor, and you can get large current. So this is the breakdown condition. So the breakdown voltage depends on P times D in DC glow discharge. Following this equation. So the B and A coefficient are the same as the above equation. Right here, A and B. And the gamma factor we have already known as the second Townsend coefficient, and which which is a property of material. Property of material. How easy the material can emit electron by ion bombardment. Okay, so this is a gamma factor. Okay, and the breakdown voltage, right? If you run the experiment and adjust the P times D and then record the breakdown voltage, you can find out this curve like a V curve, like a V curve. So to run this experiment, if you have a discharge tube with fixed distance between cathode and anode, right? And then the variable is pressure. So you can try to strike your plasma with different gas pressure. And from the voltmeter, you can record the breakdown voltage, right? And then plot this curve. So if from this curve, we can find out there is a minimum point, Vs minimum, at a certain P times D value. So it means if you have a system with a certain distance between cathode and anode, and then if you fill in gas to certain pressure, you can get small breakdown voltage, or you can start or strike plasma easily with low voltage. But if the PD value is small, or if you increase PD to this region, the breakdown voltage become higher. So it means you need higher voltage to generate plasma. And then this curve is named Paschen curve. Okay. Paschen curve. So this is from the experimental curves, and these curves are very useful for the design of DC discharge system. So this figure shows the Paschen curves for different cases. Okay. Okay. So for example, this curve is for hydrogen. So if you generate hydrogen plasma, right, with the P times D value, right, around 1 or 2, and the unit is centimeter times torr. Centimeter is the distance between cathode and anode. Torr is the pressure of gas. Okay, so if you set up your system with P times D around 1 or 2 centimeter torr, you can generate hydrogen plasma, right, with breakdown voltage less than 300 volts. Less than 300 volts. Right. And if you decrease the P times D value, you need, for example, to displace around 0.2 centimeter torr, you need a breakdown voltage above 1,000 volts. 1,000 volts. So it means for the PD value at the left side, the smaller PD value, right, compared to the 1 or 2 centimeter torr, it's difficult to generate hydrogen plasma because you need a high voltage to generate hydrogen plasma. And also, with the high PD value for the same hydrogen gas, same hydrogen gas. If the PET value is 100 centimeter tall, 100 centimeter tall, you need a voltage higher than 2000 volts to generate hydrogen plasma. Okay. And the left side of the Paschen curve is called left branch of the Paschen curve, and the right side is called right-hand branch of Paschen curve. Okay. And the reason for that, the difficulty of the to generate plasma in the left branch is explained by these sentences. Okay, because in the left branch, the P times D, right? PD is small. PD is small. So if we have a fixed distance between cathode and anode, this region means the gas pressure is small. So the gas density is small. Small gas density, okay? This part. So the possibility for collisions are very, very limited because there's no enough gas molecules within a small distance. So the possibility for the collisions are very limited. So that for effective electron impact ionization, one requires high energy electron, so that for each collisional process, they can get successful ionization of the gas. Okay, so for this part, okay, one need very high electrical field, so that the energy of the electrons is high. It becomes very high because the collisional process are very limited for the low PD region. Okay, and for the high PD region, in this region we might operate the process with very high gas pressure. Okay, so that the mean free path of the gases are very small, and the distance for the electron to travel freely is also small. So with the fixed electrical field, for a fixed electrical field, when the electron only travel for a short distance, they can just get very small energy. So if you want to increase the energy of electrons, again, you need a high electrical field. So that even though electrons just travel for a short distance, the electron can still get enough high energy to undergo electron impact ionization. Right? So for the right-hand branch and left-hand branch, okay, one always need a high voltage so that the electron can get high energy and undergo effective collisional process. Okay, any question?